this class, microelectronics. That's the textbook of the title of the textbook, or electronics. It's all about signals, and signals is information. And sometimes you see things written in terms of information being sent. It could be something that's sent as a voltage. You could have some kind of time-varying voltage signal. Could be something that's we're sending as a current. Again, some time-varying current. Either way, we could understand that there's information being sent through over time, either as a function of voltage or current, or both. And it could be analog. It could be converted to digital. But really, digital circuits are electronic. They're still electronic circuits. This course only touches around the edges of digital electronics, and even in electronics too, we just only touch the edges of digital, I think. But if you, for instance, become a digital IC designer, you really will deal with things that are analog signals. Things like rise time, noise, voltage levels. Those are all really analog issues and analog questions, especially at the high speeds that people use today. It could be your signal is coming from a transducer, like a microphone or a pressure load sensor, a temperature sensor, light sensor, all kinds of things like that. And it could be that your electronic signal, this voltage versus time kind of thing, it could be that it's coming from a fiber optic. You could be on the other end of a fiber optic. It's still a signal, and it's still something that's varying with some kind of voltage or something varying with time. So you might say our digital signals really they're different, and they're not analog signals like we're talking about in this class. So you might have a digital signal that maybe looks, you've got some kind of digital things going on, whatever it is that's coming through. I've drawn that the same way every time. But these are still actually analog signals. If we zoom in here, what we might actually see if we zoom in enough is we might see something that looks more like some ringing and some actual slope. There's a slope there. It's not an infinite slope. If we zoomed in enough, if we zoomed in further, we might actually see something that looks like that. And these kinds of the things that are happening on this edge here are very much the world of analog electronics. It's really what's happening, and you have to to worry about. Now, you might think that zoomed in thing isn't very important, and if you're writing Verilog, you're right. It isn't important. It isn't going to matter for you. If you have a digital system operating, say, or a digital system designed to operate at 1 megahertz, and it's being run at 1 kilohertz, you're really not going to have a trouble. But if you've got a 5 gigahertz design operating at 5 gigahertz, then it's a very big deal. And these sorts of rise time issues and the quality of that signal and the amount of ringing, those are really at the heart of making a digital system look like that. And the people designing ICs and things like that, it's not unusual for them to have to worry about analog sorts of issues. This book, Electronics, in the subject electronics, is not power electronics. But it's pretty closely related. And we'll touch briefly on power electronics in electronics too. In fact, I'm going to be teaching power electronics in the spring, and the prerequisite for that course is this course. So if power electronics sounds interesting to you, you may want to sign up for it in the spring. You don't need to have taken electronics 2. You don't need to be taking electronics 2 to take power electronics. I think it'll be interesting. I hope it'll be interesting. So I encourage you to take it. If this course seems okay to you, then power electronics might be very interesting. Actually, we'll touch a little bit on power electronics when we talk about diodes. So we're doing some power electronics things there too. So signal sources. I talked quite a bit about this yesterday. I'm not going to talk much about it yet today. But we could have a Thevenin representation where we've got a signal source and a Thevenin resistance, or source resistance, I'm calling it here. And we could look at that as a Norton circuit. It's perfectly identical. We're just considering that we have a current source instead of a voltage source. And the T here is meaning source. And we have exactly the same source resistance. In fact, we've got a current and we've got an output voltage. We've got an output voltage here, and we've got an output current here. So they're totally equivalent. They're the same thing. It just matters when we use them. So you may think it's not so critical. You may think that you're done with 2205 and you don't want to do circuits 1 junk anymore. But actually, it's really critical. Thevenin and Norton equivalent circuits are really, really critical. We will spend a lot of time worrying about amplifiers. We're building up in this course to getting the basic knowledge in place to make amplifiers and design amplifiers. And amplifiers are usually a voltage in, voltage out kind of thing. So usually a voltage amplifier, although they don't have to be. And for a voltage circuit, a Thevenin source makes good sense. However, a transistor is really a current source. It's a voltage-controlled current source. And so when we draw out circuits with transistors in them, they're likely to have a Norton circuit. But the thing that we're actually trying to make is a Thevenin circuit. And so we're going back and forth all the time between them, and it needs to be really comfortable and easy for you to do that. Remember that we can write the source voltage as a function of time is equal to the source current as a function of time times the source resistance. They're perfectly equivalent, and we can also say, so this is thinking as voltage as a function of current, but we can also think of current as a function of voltage through Ohm's law. They're perfectly equivalent. And most importantly, perhaps, is to realize that the source resistance, we can define it as the source voltage over the source current. Or the, well, yeah, and so in effect, we have a resistance. If we know a current and we know a voltage, then by Ohm's law, let's say it always holds. Ohm's law, it's always there. We never get to say it isn't true. It always works for us, and it's important. So if you know a voltage and you know a current, you know a resistance. Even if there is no physical resistor, even if you have a complicated circuit with all kinds of other things in it, once you have a voltage and a current, then you know a resistance, or you can express those voltages and currents, that ratio, as a current. Now it could, or as a resistance. It could be changing, right? These are both functions of time. And so we've got a function of time here, and we've got a function of time here. And because those are functions of time, it may be that this resistance changes with time, but it's still a resistance. You need to be instantly comfortable with that viewpoint and realize that in some situations Thevenin works better, and in some situations Norton works better, and so it's just whichever works best. Now, when we build an amplifier, we want to do it linearly. It's really important that it be a linear amplification. So if we have a voltage in and a voltage out, we want to linearly change it, say by 5 times or 10 times or 100,000 times, whatever it is. If we don't change it linearly, we'll introduce distortion. Distortion means we've modified the information. So our amplifier is likely a failure if it's introducing distortion. Now, they always introduce some distortion, but we at least want to minimize the amount of distortion in an amplified signal. It's also much easier to analyze. If we have a linear circuit, it's way, way easier to analyze compared to a nonlinear circuit. And transistors are nonlinear devices, so as much as we can make them linear, we will. And there's a couple of tricks and a couple of ways that we can do that. But making it linear is really, really important as far as most of the circuits we're working with. There's some other important goals like not adding noise, how fast a circuit is, bandwidth, the power it uses. Those are all important, and sometimes they can be extremely important. So what does linear amplification look like? What do I really mean by linear amplification? So what I mean is if we have a output signal, V out, which is a function of time, that we could rewrite it as A, some number A, times V in, which is a function of time. And A is a linear amplification factor. I just made that up. We call that gain. And in general, gain is output over input. So when I've got it written here, I want to multiply V in times some factor, some number, 5, 10, 100, 100,000, whatever it is, but some factor to get V out. And if I can do that, if A is a constant number that I can multiply by, then it's linear, and we've got a linear gain, which is what we're searching for. So in this case, it's V out over V in, but it doesn't have to be V out over V in. It could be current, it could be power, it could be all kinds of things. It's not always voltage gain. But we usually deal with voltage gain in this course. And we are usually working with low levels of voltage, usually microvolts or millivolts. And that introduces a big simplification later called small signal analysis. And small signal analysis takes inherently nonlinear circuits and turns them into linear circuits, and analysis becomes very easy. Just resistances, voltages, currents, maybe a few capacitors here and there. But if you can't do those basic Thevenin and Norton things, then working with the small signal approximation and transistor models and things are really going to be tough for you. So you need to make sure that you're comfortable with that and review it if you need to. There's no need for, at least I don't think there's much need for mesh node or no mesh. The mesh or node, the mesh or loop analysis methods that you learned in 2205 A lot of you can still do those. That's great. I never learned those in college. I've taught it, but I never felt terribly comfortable with those. And in fact, you don't need them. And the problem with those methods is that they don't give you much insight, whereas Thevenin and Norton actually give you some insight to the circuit. Sometimes you may be confused by that insight, but they actually do offer insight. The mesh and loop analysis methods don't really give you much insight into a circuit. So I wouldn't bother using them. I won't tell you you can't, but I wouldn't use them, and I'm not going to use them much. So the symbol for an amplifier is a triangle pointing in the direction of the amplification, basically. So we have input and output. That's a perfect amplifier, the kind of thing where we have V out is equal to A times V in as a function of time. Sometimes I'll write out and in, sometimes I'll write an O or a not and an I. But keep in mind that voltage means absolutely nothing without a reference. Voltages always need a reference. A voltage is a potential difference. It's basically an energy. It's an energy difference. And to understand a difference, then we have to have a reference. And we usually use ground or earth for voltages. Doesn't have to be ground, doesn't have to be earth, and there can be different values for ground. Earth generally refers to our planet. So if we say 5 volts, if I say, there's 5 volts on that node, or apply 5 volts, that really means, what that means is 5 volts minus earth. And this is equal to 5 volts minus 0 volts equals 5, right? So we're always assuming that earth or ground, it's assumed. We usually don't write it in. So this amplifier up here, it's really a circuit that looks like this. If it's a voltage amplifier, we've got earth, and it's really a circuit that looks like this. And so we have V in, plus minus, and we have V out, plus minus. That's really what a voltage amplifier looks like. We're looking at the gain, the circuit gain from, oh come on, from output back to input, all reference to ground, all reference to that same signal. In the lab, when you can, you should make this earth, make this ground. And the ground connection in your house or in the lab, that third prong on your electrical circuits is actually connected to usually a bar of some kind pounded into earth. It's supposed to be pounded into wet earth. It's not always easy to pound those ground connections into earth and make a good electrical connection here in Colorado. If we were in Florida, where the water table is 2 feet down, it's easy to make a good connection. But generally in a big building like this, they've done a very good job of making a good connection to earth for ground. And in your house is probably a reasonable connection too. We need to make those connections in all kinds of places because we need a good solid reference everywhere, and earth is it. So we could more generally draw this amplifier as two inputs and two outputs and connect both sides to earth. That would be even a more general amplifier. But so you just need to understand that this is really what an amplifier looks like. This is really what it is. This is what we're really building. But as I say that, it doesn't have to be connected to ground. It doesn't have to be that way. This is what's often assumed if it's not drawn in that way, but it could be drawn perfectly this way. In which case we mean that this is a fully differential or differential in, differential out amplifier. And in that case, both these lines, this one and this one, are not at ground. So we might have plus and minus on the output. And we're not talking about an Earth reference system. It doesn't have to be referenced to Earth, but if it's not shown explicitly like this, then you should assume it is referenced to Earth. Often what we really have, at least in the amplifiers that you may have used so far, op amps, what you see is this. It's the same thing. These are the same two things. It's just that we haven't drawn in a reference there. So in this case on the right, we have a differential in, single-ended output op amp. And we've referenced the output voltage. It's a single wire, and we're referencing it to ground. But it's really the same as this. If we just connected this to ground, this would be exactly identical. Fully differential in, differential out is a bit more complicated, so we're not going to mess with that too much. Although if you've got the Analog Discovery or ADAL and 2000 units that you're using, those are fully differential in. I guess they're single-ended output, but they are fully differential inputs on the voltage and scope inputs there. So a real circuit, the real world, actually you need to apply power to it. So we may have inputs to an op amp. But there's always got to be a power applied to it as well. And that's whether it's in a simulator or in the lab. There may be, say, plus VCC and minus VEE. That's the power that's applied. If you don't connect the power and if you don't turn it on, it isn't going to work. And if you're using a simulator and you've got an op amp in your simulator, if you don't connect VCC and VEE and turn them on, nothing's going to happen. So you absolutely have to connect power and make sure you have it turned on. And one of the things that I will often do when I'm troubleshooting with you is get your probe and get you to touch your probe right on that pin right there, and then right on this pin down here at VEE to see that voltage to make sure that you've actually got it attached and turned on, because it's really easy to think that you've got something turned on when it's not. This is the real thing. How should I say? This is reality for the lab and simulation. But usually in class and in the book, we'll use the ideal circuit. So we'll be talking about amplifiers that might look like this. That's ideal, with some linear gain of A. Oops. So this isn't the ideal circuit where it's thought, or where you're supposed to realize that we have power hooked up to it. It didn't get much thinner. It's easier to work with ideal, and there's a few other things about ideal circuits too. So when we use this symbol, this ground symbol, usually it means earth, but it could just mean circuit ground. So there may be a symbol with some slanted lines on the amplifier or the power supplies. Often we'll take this as meaning earth, but usually, or it's better to say ground. And ground can be different. There can be a circuit ground, which is different from the earth ground. So it could be a circuit ground. So if you're thinking about, whatever the 500-volt battery on an electric vehicle, and you have some low voltage electronic circuits to measure current and temperature and things like that sitting on your battery, they're actually their system ground for the electronics is sitting at 500 volts, and if you so you might have an amplifier sitting like that, and you've got an input, and you've got plus VCC, which is at say plus 10 volts. And you've got minus VEE, which is minus 10 volts, say. And if you measured if this was plus 10 volts, let's say, if you measured to earth, you might see 510 volts, right? A very big voltage. But if you did a different measurement, if you instead used the power supply as your reference, if you have this, however I should draw that, you've got 500 volts there. If you then measured from VCC to here, you'd see 10 volts. Because that's what this power supply is actually being supplied. This VCC is being supplied 10 volts. And that's sitting on top of a 500 volt battery. So in that case, the circuit ground is sitting at 500 volts, which is different from the earth. Usually we'll just talk about ground. But in truth, sometimes what we're really talking about is circuit ground. And later on, we're going to use a symbol. Looks like that. And we call that an AC ground. I'll explain a lot more of what that means. But this would be a ground, just like this earth ground. They would be similar kinds of things, but some specific differences in how we use them. And in small signal analysis, this AC ground becomes very important, and we use a lot and depend on that.